Hi everyone. So first, just checking, is the sound all right? Okay, I should lower it down. Okay.
You should speak loud.
I should speak louder. Okay, fair enough. Good. Hi everyone. Thanks for attending this talk. It's a pleasure for me to be presenting here, and thanks to the organizers to begin with. Today, as Jordanis mentioned, I'll be talking about solving constraint satisfaction problems using the quantum approximate optimization algorithm, which is based on recent joint work with my supervisor, Ashley Montanaro. All right, let's give some elements of context to begin with. In this work, we'll be talking about solving constraint satisfaction problems, which are a very frequent class of problems in many applied disciplines. Maybe the cliché example is logistics. On the other hand, we'll solve CSPs using the quantum approximate optimization algorithm, commonly abbreviated QIOA. This algorithm was originally designed to address constraint satisfaction problems, and more precisely, to maximize the number of satisfied constraints. However, in this work, we'll use the algorithm differently. Namely, we'll want to satisfy all constraints. So that's a bit different from the usual. Sadly, many constraint satisfaction problems are actually computationally hard, meaning both classical and quantum algorithms are expected to take exponential time to solve them. The relevant question then becomes, which of the classical or quantum algorithm has the smallest scaling exponent? As it was originally introduced in 2014, QIOA was briefly believed to outperform the best-known classical algorithms at the time for a certain class of constraint satisfaction problems. Sadly, this claim was soon falsified as better classical algorithms were introduced, and since then, any speedup of QIOA over classical has remained elusive. In this work, we then try to address the question, can QIOA achieve a speedup for certain constraint satisfaction problems? Well, we'll proceed as follows to answer this question. We did the introduction, so the next step is to discuss the problem we'll try to solve and how we implement QIOA for that problem. Then we'll describe our results, which are both analytic and numerical. Finally, we'll conclude on what we learned from this work and what are future perspectives for improvement. All right, let's start with the problem and the algorithm. The constraint satisfaction problem we looked at in this work is KSAT. This is a fundamental problem in classical optimization, and most importantly, is an NP-complete problem, which means again that both classical and quantum algorithms will find it harder to solve that problem. More precisely, and you don't need to understand the details at this point, that's just to fix some notation, a KSAT instance is characterized by three numerical quantities. First, it's an optimization problem on n Boolean variables denoted by x. Then, this constraint satisfaction problem consists of m clauses or constraints, commonly denoted by sigma. Finally, each clause contains k variables, that's the k in KSAT. An instance of KSAT is said to be satisfied if all of its clauses or all of its constraints are. And once again, we do want to satisfy all constraints. All right, now we've described the problem. Let's speak about the algorithm to solve it, namely QIOA. So many of you may be familiar with the principle, but let me give you a brief reminder. The general principle of QIOA is to alternate between two types of Hamiltonian evolution. On the one hand, you have a Hamiltonian HC in equation 2 that encodes the constraint satisfaction problem to be solved. On the other hand, you have a transverse field Hamiltonian HB in equation 3, which is just a problem-independent transverse field Hamiltonian. And you then evolve alternatively under the two using evolution times that are commonly denoted by gamma and beta. After preparing this state, you measure it in the computational basis to obtain a candidate solution expressed as a bit string, because there's a problem on Boolean variables, and hopefully this gives you a satisfying assignment to your CSP. Note that QIOA is a variational quantum algorithm, which means that parameters beta and gamma, which people sometimes call QIOA angles, need to be optimized. And that's a major challenge of using the algorithm in practice, because, for instance, what if optimizing this continuous variable problem is as hard as solving the original constraint satisfaction problem? This can be an issue. In this work, we partially address this issue by running with fixed parameters, which means that we optimize parameters once and for all, and then we run over all instances, over all constraint satisfaction problems with the same parameters. So we skip the training phase in some sort. Okay, so how does this apply to KSAT, this QAOA? Well, to define QAOA, one first needs to define a cost function that will enter the problem-dependent Hamiltonian. In this case, we make the usual choice of choosing the cost function as counting the number of violated clauses, the number of clauses that aren't satisfied. So this gives you this diagonal Hamiltonian. This is pretty standard. However, what is less standard is the cost function we choose to train. Because the usual choice in the literature is to use the number of satisfied constraints, the expected number of satisfied constraints when you sample over the quantum state, and to maximize this number. But here, we actually want to maximize the success probability of the algorithm, the probability of finding a satisfying assignment. Now, this poses a major problem that this cost function is hard to evaluate, whether classically or even on a quantum computer. Because to estimate this probability, you'd first need to get a satisfying assignment, which, if you do, you've already solved the problem. So how are we going to address that? Well, a natural idea you may consider here is, what if things get easier if you consider an average problem instance? And this idea is not new. It was actually considered in the context of QAOA in a paper that was presented in QIP2023, where the authors show that for another optimization problem than KSAT, averaging over instances made things much easier in terms of analytic results. But to define what an average instance probability means, one first needs a notion of random instance. Fortunately, this concept comes ready-made in the classical optimization literature for KSAT. Simply speaking, a random KSAT instance is an instance of KSAT where all clauses are drawn independently and uniformly at random among all possible clauses. Interestingly, this random ensemble of constraint satisfaction problems admits a so-called satisfiability phase transition, which means that while the closest to variable ratio crosses a critical threshold, the instance goes from being satisfiable with high probability to being unsatisfiable with high probability. However, even before you reach this so-called satisfiability phase transition, you already cross an algorithmic phase transition where classical algorithms start to struggle. Before this algorithmic transition, they take polynomial time to solve the instance versus exponential time after this algorithmic transition. Therefore, this sweet spot between the algorithmic ratio and the satisfiability ratio is an interesting regime to consider because algorithms struggle, to speak simply, and on the other hand, you know the instance has a solution, the problem has a solution, so it makes sense to find a satisfying assignment. All right, that's about it for random KSAT. And as a reminder, the reason why we did that was to define the notion of an average instance success probability for the quantum algorithm. So we simply define this probability as an equation 8, taking the instance-wise probability and averaging over this random KSAT ensemble that we just defined. Now, doing that, and assuming this leads to some analytic result at all, we've created a new problem, because averaging over an instance doesn't give you exactly the running time of the algorithm. I'll explain that. For a single instance, what you care about is indeed the running time, which can be expressed as the inverse of the success probability for that specific instance. However, after you average this inverse probability over instances, assuming they're satisfiable, you only get a lower bound on the running time, just because the inverse of the expectation is not the expectation of the inverse. Still, we'll work with this limitation in our approach and show it gives decent enough results. All right, now we've discussed random KSAT, which is our constraint satisfaction problem, and how we will apply QAOA to it. Let's talk a bit about our results. Let's then start with the analytic results. So our main technical proposition can be schematically summarized as follows. You're looking at KSAT, which for technical reasons has to be a power of 2 in our case. So for instance, 2-sat, 4-sat, etc. And you're looking at constant depth PQAOA with fixed parameters beta, gamma. We showed that for sufficiently small variational parameters, this average instance success probability that we just defined admits an exponential scaling in the instance size n. Furthermore, you can compute this scaling explicitly by finding the fixed point of a function of 4 to the power p complex variables. Okay, so assuming this procedure works, what can we do with it? Well, we can do what we just said earlier, namely use this probability that we can now estimate to optimize QAOA over parameters beta and gamma once and for all, which is another advantage of going to average instance, because now you can optimize it in average. So that's basically what we did. However, as a funny result of that, we found that this complicated analytic procedure gave equally satisfying result to a much more trivial idea, which was to basically generate a bunch of random instances, estimating the success probability by empirical averages and relying on that estimate to just optimize over parameters. So that was quite a surprising finding, especially since with the limited number of instances we use, we get a poor estimate of the actual success probability, but still good enough variational parameters in the end and comparable to the analytic procedure. All right. So now we've discussed what we can do with the analytic result. Let's say a few words of the proof techniques. So the proof, briefly speaking, rests on the analysis of a special mathematical object which we call a generalized multinomial sum. So that's not a canonical name, we just made it up, sort of. And just to explain what it is, here is a binomial sum to begin with. I'm sure this is familiar. You can evaluate it using Newton's binomial theorem. And this generalizes to a multinomial sum, whereby instead of summing over two integers n0 and 1, you sum over a bunch of integers ns, which are indexed by some finite set, capital S. And the binomial theorem generalizes to the multinomial theorem in this case. So that's easy to evaluate. There's no difficulty here. Now, what we showed is that the average instance success probability of QAOA for K-sat can be cast to a sort of generalized multinomial sum, which is explained for the case of 2-sat in equation 15. So as you can see, it starts pretty much like a standard multinomial sum. You have this binomial coefficient, you have something to the power ns, and so on. However, the difficult part is the exponential, where you have inside a quadratic polynomial. And then you can't use the multinomial theorem anymore to evaluate that. To be fair here, we should point that recent work was also published that estimated sums like that, once again in the context of QAOA, but for a different optimization problem. And we think that the techniques that we present here are somehow different and not applicable under the same assumptions. All right. So very briefly speaking, how do you tackle that for the simple case of random 2-sat? Well, the main issue here is that you have this exponential with a quadratic polynomial inside, and we'd like it to be linear. So we make it linear. And how do we do that? By taking a linear polynomial, multiplying it by a Gaussian variable, and averaging over that Gaussian variable. But now the polynomial has been made linear. You can perform the sum inside the expectation as you would a standard multinomial sum. After a few changes of variables, you then obtain the final equation where you integrate over a bunch of variables theta. And the integrated function is of a special form, namely the exponential of n, the instance size, times a function independent of n. And I'm sure many of you know that there is a standard method, especially in physics, to estimate such integrals. It's called the saddle point method, or the stationary phase approximation, or also Laplace's method. So this is very standard, and that's basically how you get the existence of an exponential scaling. Okay. Now we're done with the analytic results. So what about numerics? And I'm sure at this point you're all asking how well do these analytic predictions match with numerical experiments? First, I'd like to say a few words of methodology that at p equals 1, if we want to do numerical experiments, we can't really evaluate exactly the success probability for a finite size, because all these analytic results we showed, they hold in the infinite size limit only. So we're somehow limited to estimating success probability at finite sizes using empirical averages. So that's basically what we do. For KSAT, and with a fixed closest to variable ratio, which we choose as satisfiability threshold to make the problem hard, we generate 10,000 random instances for small sizes comprised between 12 and 20. And for each of these sizes, we estimate empirically the success probability of QAOA. And yeah, just to say, with these choices of number, you get an empirical 1% relative error on the success probability. So you can definitely compare to analytic results. And here are the results of our comparison. The solid dots here are our numerical experiments points, while the solid lines are exponential fits for these points. So first of all, it appears that although the sizes are quite small, you clearly see the exponential scaling of the success probability average over instances. More importantly, the dotted line represents our analytic exponent that we find with our procedure, and you can also see that despite the small sizes, these exponents match pretty well. So the analytic procedure does seem to predict correctly the success probability of QAOA, even though we're far from the infinite size formally. So we were kind of encouraged by these initial results, and this motivated us to benchmark QAOA against classical solvers. Now, up until now, we had considered the success probability, but to do these benchmarks in a more reliable way, we chose to consider the median running time instead, because remember from the beginning of the talk, that's what we're ultimately interested in. How long does the algorithm take to run? And for that purpose, the median running time is a good candidate. Still, a drawback of that is that we have no theoretical control over the running time, but we use our belief that we're already in the asymptotic regime to trust these benchmarks. Okay, so same methodology and everything. So what does this give us? Well, the results are expressed in the plot and in the table, where the table tells you about the exponential fit for these running times. And what we observe is that first, we still do have these exponential scaling behaviors for both classical and quantum solvers. And more interestingly, QAOA with as few as 14 layers does seem to outperform the best classical contender, which for this parameter regime happens to be an algorithm called Worksat LM. All right, and if you increase the number of layers even further, say to 60, you can do even a little better. But to be honest, some work remains to be done to determine the ultimate limit of the scaling exponent, like how much better you can do. All right, so what did we learn from this talk? So as a reminder, in this paper, we considered QAOA in a different setting from the usual, in that we try to maximize the probability of success versus the number of satisfied constraints as is usually done. Trying to do that, we proved rigorously the existence of an exponential scaling for the success probability, average over instances, and we showed how to practically compute this success probability. We validated this theory using extensive numerical benchmarks, which show good match. And a lesson from these benchmarks is that the match exists even if we're very far a priori from the infinite size regime. So with n equals 12 or n equals 16, it's already very good. An important lesson that we learned from that is that QAOA, using constant depth, does seem to outperform Grover's algorithm, which requires exponential depth. So you shouldn't be using Grover to solve structured constraint satisfaction problems like KSAT, for instance. And maybe more optimistically, QAOA does appear to have a scaling advantage over leading classical algorithms, although more work is required to determine the ultimate limitations of this scaling. I'm done for the talk. Thanks for your attention. And yeah, further announcement, my supervisor startup, Facecraft, is currently hiring for postdoc and intern positions. So feel free to reach out. We have a stand and they have some swag. Thanks very much.
Thanks a lot, Sami. Thanks for the talk. Thanks for the publicity. So let's get some questions. First one.
Your numerical results were for 8 sat.
Yeah, 8 sat at satisfiability thresholds.
Do you have any results for 3 sat?
So we do have numerical results for 3 sat that we can't exactly compare to theory, though, because we're limited to powers of 2. But we do have results for 4 sat, for instance.
And what was the aspect ratio? Number of clauses divided by number of variables?
For 4 sat? Yeah, for 4 sat, it's 9.93. We always work at satisfiability threshold in all cases. Yeah.
Yeah, thanks for the talk, and it was really interesting, the results and your explanations. So I had the same question as he asked just now, that what would be like if it is not the exponential of 2, like, you know, but I mean other instances. But I also have a question regarding to you said that the bounds holds for like the fixed parameters, right? I mean, when the parameters are fixed for certain instance of card, but what will happen that if you change the parameters and, you know, like in a different...
So if you change which parameter, say K, R?
Yeah.
Yeah. Good point. For instance, a good question you may ask is, what happens when R crosses the algorithmic threshold or the satisfiability threshold? Qualitatively, if we run, say, at constant parameters, we don't see any qualitative change in the exponent when that happens. So that may be surprising. But also, I'd like to attract your attention that even for 2 sat, constant depth QAOA has an exponential time. So, you know, maybe you don't see things happening, but that's because it always has exponential scaling, which some classical algorithms obviously don't have for 2 sat. So, yeah.
Yeah, thanks.
There's a question here in the front.
Oh, hey, thank you for the wonderful talk on Boolean satisfiability. I was wondering if you ever explored comparing QAOA for solving SAT problems with using variational quantum eigensolvers for SAT problems.
So the VQA, and so you mean the VQA, say, with a problem independent ansatz?
Yeah.
Yeah. Okay. No, we didn't do that. That would be interesting, and that would be an interesting complement indeed. We didn't do that.
Yeah. All right, thank you. Yeah, we can discuss after.
Any more questions?
So when you optimize these angles, beta and gamma, do you, how do they look like once you find them? Do they have some pattern?
Yeah, there's more detail in the paper, but yeah, there's definitely some pattern that you see similar to the pattern you'd see in other CSPs like Max Carter. Yeah, it's still an open question to understand this pattern, actually.
Thank you for the wonderful talk. So the exponents that you showed on one of the slides, what would be the exponent for Grover, and what is the degree of the polynomial speed up here that we see?
Yeah, so for Grover, it would be 0.5 because that would just be a quadratic. Well, say, okay, you can use Grover-like routines to accelerate, say, state-of-the-art classical solvers. But if you use just trivial Grover, that would be 0.5. So that's, I would argue, a mild polynomial speed up over Grover then. Yeah.
Hi, yeah, it was a very interesting talk. So we heard in this room a couple of talks ago that noise is very constraining for QAOA. So can you say anything about what happens if you add noise? So I think you had like a perfect quantum computer, right, in your simulations?
That's a very good point, actually. To be fair, I'm not entirely sure that in the regime we're running at, say, KSAT, very dense and so on, we're considering it in the NISC, say, framework at all. But yeah, incorporating noise, though, would be an interesting complement to the study. But yeah, the dense regime we're running in seems to make it pretty challenging.
But do you think your methods could be used there at all, or would it be like very difficult to adapt?
A possible way of sort of solving it would be trying to show advantage for other problems, which, for instance, may require lower closest to variable ratio to show hardness. Yeah.
Okay, one last question.
Thank you. So thank you for your talk. My question is about that figure. What do you mean by, how you estimate this running time? What do you mean by running time of two so different things, like these classical solvers and the quantum one? How you define the running time?
Yeah, so for the classical solvers, it's basically evaluated. So, okay, many of these classical solvers are branch and bound styles of algorithm. So you're basically counting the number of branchings versus in quantum, the number of time you query the formula via the Hamiltonian oracle. Yeah.